All right, so as we're doing our electron configurations, what we're seeing here is the more electrons you're putting in there, things are getting kind of complicated and not, well, I wouldn't know if it's more complicated, it's just more tedious how many electrons to put in there. So let's do electron configuration of sodium. We've got 11 electrons to put in there. Okay, we know we go into the 1s2, then 2s2, then 2p6, and that's 1, 6, 7, 8, 9, 10. There's 10 of the 11 electrons. The question is, where does that 11th electron go? If you're looking at your little cheat sheet of the next orbital it goes in, yes, it goes in the 3s orbital. So that will be 3s1 for that last electron. But something we notice, 1s2, 2s2, 2p6 is the same as neon, the noble gas, 1s2, 2s2, 2p6. So what we're going to do is we're going to come up with a little shortcut. We call it the noble gas core shortcut. And what we're going to say is, all right, I'm going to, whatever element I'm looking at, I'm going to find the closest noble gas preceding that element in terms of atomic number. And I'm just going to write that in brackets. And so if we're looking at sodium, the previous noble gas is neon. So I'm going to write, instead of 1s2, 2s2, 2p6, I'm just going to put neon in square brackets. And that's going to be neon core 3s1. All right. If we look at the electron configuration for phosphorus, phosphorus has 15 electrons. We could do the whole thing, 1s2, 2s2, 2p6, 3s2, 3p3, or we could just say, all right, this whole part right here is neon core. Neon core, 3s2, 3p3. What you may be noticing is when we do the noble gas core shortcut, the only thing we are writing are the valence electrons. So this is one reason why noble gas core shortcut is used so much, because one, it's quicker, but two, the only electrons that you worry about, the only electrons you can really see are the valence electrons, and those are the ones that do all the chemistry. All right. Now it turns out there's an even easier way of doing this, as long as you remember a few tricks. What if I wanted the electron configuration of iodine? Iodine has 53 electrons in it. Can you see it's going to be rather tedious if we are going to do it this way, if we're going to look at our energy levels? If we're looking at 53 electrons, question for you, where in this chart are we at 53 electrons? It's going to take a lot of counting, and I've watched a lot of Sesame Street, but I don't care. It's more counting than I want to do. So, good news. We have the chemist's ultimate cheat sheet, the periodic table. Let's look at our periodic table here, and we'll notice some things. All right. Recall how many electrons are possible in any orbital? Well, 2 electrons. The 1s orbital can only have 2 electrons in it. Well, the first electron belongs to hydrogen. Helium would have 2 electrons, which is this one, and this one over here for helium. Next comes the 2s orbital, which could have 2 electrons. So lithium has an electron in the 2s orbital, and beryllium has an electron in the 2s orbital. And then we've got the 2p orbitals. Recall how many electrons can be in 2p orbitals? 6 electrons total, because we've got 3 of those orbitals, 2 electrons per orbital. Note, how many elements do we have here? Each element adds an electron. 1, 2, 3, 4, 5, 6. So what we see here is this side of the periodic table, we call these the s block elements because the valence electrons are in s orbitals. This is the D block because the valence electrons are in the D orbitals. The last electrons get put in the D orbitals. And this is the P block because these are where the P orbitals are. And here is the F block. Just so we're really clear on this, if your orbital is D, what is the quantum number L? Let me think. Well, S orbitals, L is 0, P orbitals, L is 1, D orbitals, L is 2. So if it's D orbitals, L equals 2. If L equals 2, what are the possible values of M sub L? Well, if L is 2, M sub L's are -2, -1, 0, +1, +2. I just counted 5 orbitals. 5 orbitals, 2 electrons per orbital, which means you can have 10 elements represented. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F orbitals, you have 14 elements represented down here. Okay. So note that the periodic table is also pretty much arranged by the last couple of electrons that get put into the atom. And so when we're looking at this, what we can tell is that this is our n equals 1 level. Here is n equals 2 shell. Here's n equals 3 with the 3s subshell, and then way over here is the 3p subshell. Here is n equals 4, so along this side here I write down my principal quantum numbers, and this works really well. The 2 little tricks to remember is after the n equals 4 s orbitals, the next d orbitals you come to are the 3ds. So make sure if you're numbering a periodic table 1, 2, 3, 4, 5, 6, 7, you do 3, 4, 5, 6 here. And with the f orbitals, it's 4 and 5. All right. But what this does is if I want to write the full electron configuration for iodine, I just have to find iodine on my periodic table. It's right here. So I just need to start up here and work my way down to iodine. And we do it like this, all right? Let's take a look. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p, 1, 2, 3, 4, 5. So using the periodic table, I don't have to really keep track of counting all my electrons. I can just use the periodic table and go through and get the electron configuration that way. It just makes it, to me, a lot easier using the periodic table to do it. So, okay, iodine, what do we have here? Well, using my periodic table, I said 1s2, 2s2, 3p, oh no, not 3p, 1s2, 2s2, 2p, 2p6. Okay, thank you periodic table for helping me. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. All right. What if you're trying to do this without the periodic table? What if you're just trying to memorize that little chart you had and the diagonals, and we're just trying to keep count of electrons? That's a lot of numbers to keep count of. Not that it's hard, it's just tedious. Periodic table makes it easier, I think. All right, and question, what if you wanted to use the noble gas core shortcut? Well, a periodic table makes that even easier. Here's iodine right here. What's the closest noble gas? Has to be previous noble gas. Well, krypton. If we're in the n equals 5, the noble gas for n equals 4 is our closest noble gas. So krypton is our core. Krypton core. Note, looking at our table here, krypton ended at the 4 p's. So this would be 4p6, and then on our table we're up to 5, 5s2, 4d10, 5p5. 5s2, 4d10, 5p5 for the electron configuration of iodine using the noble gas core shortcut. All right. So now that we've done that, I'm going to cut this video a little short because we're going to start to get into some complications. Let's just call them complications.